being here at the maths faculty in Cambridge with some of the most famous physicists in the world is absolutely amazing. Every day I come here and I see those amazing buildings. Somehow it sort of radiates knowledge.
No matter what you want to think about, you've got someone who's a world expert to talk to.
Yeah, Stephen Hawking is definitely a draw. Whenever he comes in, it never gets old. It's always still quite exciting when he comes into the department.
Of course, it's been amazing to see Stephen Hawking close up over so many years. But more than that, of course, he's a singular individual. He's an inspiration to everyone. One of his mottos is never give up.
The biggest and most interesting thing is the whole universe. How does the whole universe work? How does it really fit together? What's the sort of clockwork behind it that makes it run the way it does?
Curiosity is essential to being human. From the dawn of humanity, we've looked up at the stars and wondered about the universe around us. My Cosmos group is working to understand how space and time work from before the first trillionth of a second after the Big Bang up to today, 14 billion years later.
The Cosmos group focuses on the most extreme events in the universe, when the basic fabric of space and time is shaken up.
We are searching for tiny signatures in huge data sets to find clues that will unlock the secrets of the early universe and of black holes.
Without computers, what we do now would be impossible. Now, the data sets are getting so big, there's so much information. Some of these data sets are billions and billions of galaxies.
In both cosmology and in relativity, we face this deluge of new data that presents us with a lot of challenges computationally. So we were pleased when HPE was able to bring many more resources to in-memory computing.
In-memory computing definitely helps us to do this a lot easier because it enables us to test our algorithms quickly and easily.
I mean, it's the perfect system for me. It's almost designed specifically for my work.
It's so flexible. It allows you to ingest very large data sets and act on them immediately. It allows you to try out new ideas, new algorithms, to innovate and develop your codes faster. So it gives us a competitive edge in a very fast-moving field.
Academia is a fiercely competitive industry. For you to stay ahead of everyone else, you've got to be pushing the boundaries. Having the right architecture behind you and the right systems behind you is a really key part of that.
We work hand in hand with the scientists, getting a new system to help them even further in their scientific endeavors is just fantastic.
The first ever direct detection of gravitational waves announced last year caught me by surprise, because I did not expect it so soon. The signal found by the LIGO experiment of two merging black holes marks the dawn of a new era of gravitational wave astronomy.
It was really big news. Yeah, it opens up a completely new field.
A billion years ago, two black holes in a distant galaxy, they merged together. The gravitational effect of this was so strong that it actually created these ripples in space-time.
The gravitational waves traveled through the universe, and we measured those gravitational waves in our detectors, and we could predict the signal precisely. We've done very theoretical research for a very long time, and we can now suddenly take all of our theories, take all of our computer simulations, etc., look at the data on the fly and compare them to reality. I mean, this is what we want to do as physicists.
Within memory computing, we can keep up with the flood of new data, and we can keep ahead because we are free to innovate.
It allows us to do bigger simulations, more accurate simulations, and to really test our theory at a tighter and tighter level. So that's where shared memory computing really is the key advantage for us.
Whip up a code, no matter how weird or complicated the idea is. You don't have to worry about how much memory you use doing that, and you get some idea of whether your idea even works.
It's great because we can get students who, with a minimal amount of programming introduction, can actually use the system and do large-scale problems and get solutions.
The field is moving too fast to wait until we are all advanced programmers.
We want to be focusing on the science and on the discovery and testing our ideas.
The universe really is the ultimate laboratory for testing our ambitious ideas about the fundamental building blocks of matter and of space and time.
You know, there's not that many huge mysteries left in science out there, and we're really living a time where we should get them.
But this high-precision science and our complex theories will only be able to confront each other using powerful computers. Without supercomputers, we would just be philosophers.